We live in a world absolutely humming with connections, don't we? I mean, from the phone in your hand to, well, the global internet, our lives and work have this amazing constant dependency on networks.
They really are the invisible infrastructure, aren't they?
Yeah.
Connecting us across the room or, around the world, letting us share everything from silly cat videos to really mission-critical data.
And today we're pulling back the curtain a bit. We're taking a deep dive into the fundamental building blocks of these essential systems. We've got a stack of material here, foundational concepts, overviews, some Geeks for Geeks notes, even excerpts from a CompTIA study guide.
Yeah, it's all focused on getting to grips with the absolute basics. What networks are, the different types, based on how they're structured, how much ground they cover, and then how they're physically laid out.
Right. Our goal for you listening in is pretty simple. By the end of this, you'll have a really rock-solid base. You might get some aha moments about the tech you use every single day.
And hopefully feel much more comfortable navigating this essential landscape. It's kind of like a shortcut to being genuinely well-informed about something you interact with constantly.
Sounds good. So let's unpack this. We'll start at the very beginning, the core idea of what actually makes a network a network.
They'll branch out, talk about size and scope, how the devices relate to each other, the actual physical map of the connections.
And wrap up with some key design stuff, including how things are evolving with virtualization.
Okay, ready when you are.
All right, first things first. Based on our sources, what's the simplest definition of a network?
At its absolute heart, it's just two or more interconnected computers or devices. We often call these hosts or maybe nodes.
And the key is they're connected so they can communicate.
Exactly. And crucially, share resources. That sharing aspect is really the whole point.
Yeah, that makes sense. It seems obvious now, but without a network, sharing, say, a file or using just one printer would be incredibly clunky.
Totally. Imagine needing a USB stick, the old sneaker net, right?
Yeah.
Just to move a file across the office. Or buying a printer for every single desk. Networks solve that basic problem.
Sharing data, applications, printers, that internet connection.
All of it. And networks can be super simple, just two laptops connected, or, mind-bogglingly huge, like the internet.
They scale incredibly. Now, you mentioned hosts or nodes. What exactly counts as a host these days?
Well, the term host is used pretty broadly now. Basically, think of it as pretty much anything that gets an IP address and connects to the network. Your workstation, a server.
Even a smart fridge, maybe.
Potentially, yeah. But historically, it's interesting, the term came from mainframes. They were the original hosts. And everything else was just a dumb terminal connecting to them.
So the meanings evolve. Anything with an IP address on the network today?
Pretty much, yeah, for our purposes here. Workstations, servers, network printers, IP phones.
Got it. So interconnected devices that share. That's the core. Now, one of the main ways we categorize networks is by, well, how much physical ground they cover, right?
Right. This gets us into the different network types. The one most people know, probably have at home or use at work, is the local area network, the LAN.
Okay, the LAN. So this is confined to a pretty small space, like an office floor or my house.
Exactly. A single room, a department, a whole building, your home. That's LAN territory. Characterized by limited distance, usually we're talking hundreds of meters up to maybe a few kilometers.
And because the distances are short, they can be really fast.
Very fast, yeah. Megabits, gigabits per second. Even faster now. You're using dedicated cabling, often copper Ethernet or fiber, so speed isn't usually the bottleneck. And typically the organization or the homeowner owns the whole setup.
And the purpose is mostly local sharing. Files, printers, maybe a shared internet connection for everyone.
Spot on. Resource sharing, maybe some centralized management, shared internet access. Common tech includes Ethernet, as we said, and Wi-Fi, which is really just a wireless LAN or WAN.
I see. And our sources mention that while modern LANs aren't as restricted by distance as older ones, breaking them up still helps.
Yeah, sometimes you'll hear the term work group used, maybe in older contexts, to mean like a logical segment of the LAN for administration. It just helps organize things. It's different from the Windows security workgroup, though. More about the physical or logical grouping.
Okay, so you have a LAN, maybe a few LANs in different parts of a building, but how do you connect those LANs together without just making one giant, messy network?
That's where the router comes in. Routers are the key devices specifically designed to connect different networks. They direct traffic between separate LANs.
So they keep the LANs separate for performance, but let them talk when needed.
Precisely. It keeps each LAN manageable and efficient, but allows communication across the whole organization or even out to the internet.
Got it. So connecting LANs with routers is how you build bigger things. And if you scale up from, say, one building to connecting LANs across a whole city.
Now you're likely talking about a metropolitan area network, or MAN.
A MAN. Okay, covering a city or metro region.
Yeah, it connects multiple LANs within that larger area. One source even called it a concentrated WAN. Often uses high-speed connections like fiber optic lines, sometimes called metro optical, or powerful wireless links.
And you might be leasing lines from a phone company or carrier for this.
Often, yes. Think about connecting different university campuses spread across a town, or maybe all the city government offices. That's a man's job.
Okay, and there's another one that fits between LAN and MAN 1, the CAN.
Right, the Campus Area Network, CAN. This covers a specific defined campus like a college or big corporate park with multiple buildings.
So it's interconnecting the LANs within those different buildings on one site.
Exactly. Bigger than a single LAN, but usually smaller than a MAN or WAN, and typically owned and operated by that single organization. You'll often see a high-speed backbone, maybe fiber, connecting the buildings, and widespread Wi-Fi across the campus.
All right, local, campus, city. Now for the really big one, the wide area network, the WAN.
The WAN is where we connect networks over huge distances across countries, continents, even the whole globe. The classic example, the ultimate WAN, is, of course, the Internet.
Right. The Internet is just a massive WAN made of countless smaller networks connected together.
You got it. The key differences from a LAN are the vast geographic distances and the scale. WANs link locations that are far apart. They absolutely need routers at the edges to handle traffic between all these different networks.
And historically, they were slower and pricier than LANs.
Generally, yes, though that gap is closing with things like fiber broadband becoming more widespread. But connecting continents still involves complex infrastructure.
And the term internetwork just means connecting a bunch of networks, LANs or WANs, using these routers.
Yep. In an internetwork, your computer uses its logical address, its IP address, to find another computer, even if it's on a completely different physical network halfway across the world, thanks to the routers in between.
And WANs can be distributed, like the internet, or more centralized, like a company connecting branches back to HQ.
Both models exist. And connecting these far-flung sites requires a whole mix of technologies, often provided by carriers, things like dedicated leased lines, fiber optic services, satellite links, various broadband options, and specialized carrier services like MPLS, which we'll get to.
Okay. Let's shrink back down again for a second. What about the network that's literally right around me, connecting my phone to my headphones?
That's your personal area network, or PAN. Smallest type, very short range, usually just a few meters around you or your immediate workspace.
Like Bluetooth connecting my mouse, keyboard, headset.
Exactly. Connecting your personal gadgets.
Yeah.
Laptops, phones, headsets, smartwatches, maybe a nearby printer. The purpose is simple device-to-device connection. Technologies are usually short-range wireless, like Bluetooth, sometimes infrared, Zigbee, Z-Wave.
Could even be a USB cable connecting my phone to my computer.
Technically, yes, that can function as a very small wired PAN for things like data transfer.
Okay. We've covered networks based on geography. Now let's dive into a couple of specialized network types our sources mention. First up, the storage area network, or SAN. This sounds different.
It is quite different. A SAN is a high-speed network built specifically for connecting servers to centralized storage devices. Think big arrays, like banks of hard drives or SSDs.
So this isn't for my laptop to grab a file?
Not directly, no. This is server to storage. It provides what's called block-level access. Imagine the server seeing the storage almost like a directly attached local drive, but over a very fast network. It's super efficient for things like databases or virtual machine storage.
How's that different from, say, a network drive I might map on my PC?
That's usually network-attached storage, or NAS, which provides file-level access like accessing a shared folder. SANs operate at a lower, more fundamental level. They use specialized tech, most commonly fiber channel, but also ISCSI, which runs over standard Ethernet.
And you really only find these in data centers.
Pretty much exclusively, yeah. They need high speed, high reliability, and you keep their traffic separate from the regular LAN traffic to guarantee performance. Crucial for big operations needing fast, dependable storage.
Makes sense. Okay, rounding out these network types, especially in the WAN world, we have a few more modern or specific terms: SD-WAN, MPLS, and MGA. Let's start with SD-WAN.
Right, SD-WAN, or Software-Defined Wide Area Network. This is a newer way to build and manage WANs. instead of configuring each connection point and device manually and separately.
Which sounds complicated.
It can be. SD-WAN uses a central software controller. This controller manages all the connectivity, the devices, the services across your whole WAN. You can use any type of connection, MPLS, regular internet broadband, LTE, whatever you have, and intelligently route traffic over the best path.
So it's like virtualizing the WAN itself, making it smarter.
That's a great way to put it. It makes managing complex WANs much simpler, more agile. The software can look at real-time conditions like if one link is slow or down, and reroute traffic automatically based on application needs.
Wow, okay. So benefits are easier management, maybe better performance.
Definitely. Simplified management, better application performance, much more flexibility to add or change sites, and often cost savings because you can use cheaper internet links more effectively, maybe reducing reliance on expensive private lines. It's a big deal in enterprise networking now.
Cool. Now, MPLS, multi-protocol label switching, you mentioned this earlier, sounds like a core carrier thing.
It is. It's a technique used by service providers and large companies to make their WANs faster and more efficient. The core idea is pretty clever. Instead of every router having to look up the full, complex destination IP address to figure out where to send a packet.
Which takes time.
Right. With MPLS, when a packet enters the MPLS network, it gets a short label attached. Inside the network, the routers just look at this simple label to forward the packet really quickly. The label might get swapped for another one along the way, but it's always a fast lookup.
Ah, like putting a special sticker on a package inside the sorting facility, so handlers just glance at the sticker, not the whole address, until it reaches the destination city.
That's a perfect analogy. Exactly. It speeds up the forwarding process significantly. MPLS also offers other benefits like better traffic engineering, forcing traffic down specific paths, quality of service for prioritizing things like voice or video, redundancy, and VPN support.
Very useful. Okay, last one in this group. MGRE, multi-point generic routing encapsulation. Sounds technical.
It is a bit. It's a type of tunneling protocol. You often see it used in dynamic VPN setups, particularly something called DMVPN, Dynamic Multipoint VPN.
Okay, what problem does it solve?
Think about connecting many remote offices back to a central HQ and maybe wanting those offices to be able to talk directly to each other securely. The old way was setting up individual, static, point-to-point tunnels between every pair of sites.
That sounds like a lot of configuration if you have dozens of sites.
A configuration nightmare. Exponential growth. MGRE helps solve this. It allows a single interface on a main router, like the one at HQ, to handle multiple VPN tunnels dynamically. It can build tunnels on demand when one site needs to talk to another without needing every single possible connection pre-configured.
Ah, so it makes large VPN deployments much more scalable and manageable.
Precisely. It encapsulates the user data securely inside these GRE tunnels, but in a much more dynamic and scalable fashion. Key for efficient hub-and-spoke or even partial mesh VPNs.
Whew, okay. That's a really comprehensive look at network types based on scale and purpose. Now, let's shift gears slightly. Let's talk about how the devices on a network interact the network architecture.
Right. This isn't about the physical map so much as the relationship model between the devices. Our sources highlight two main architectures, peer-to-peer and client-server.
Okay, let's start with peer-to-peer, P2P. What's the vibe there?
P2P means all computers, the peers, are equals. There's no central boss, no dedicated server. Any computer can potentially act as both a client, asking for stuff, and the server, providing stuff to others.
So if I want to share a file from my machine, I just set the permissions on my machine.
Exactly. The computer that has the resource controls who gets access. This model can work okay for really small setups, maybe a few PCs in a home office sharing files or a printer directly. Think older Windows workgroups or even file-sharing apps like BitTorrent operate on P2P principles.
But it sounds like it might get messy quickly. What are the downsides?
Oh yeah, big downsides as you scale up. Security becomes a major headache trying to manage who has access to what on every single machine. Forget it. Central backup is really difficult because data is scattered everywhere. Performance can suffer if lots of people are trying to access files on one person's desktop, and just finding things can be hard without a central directory.
Okay, so P2P has pretty significant limitations for anything beyond a tiny network. What's the alternative?
The dominant model, especially in business and larger networks, client-server. Here, you have very distinct roles. You have dedicated servers whose whole job is to provide services.
And clients are the machines that request those services.
Correct. You typically have one or more central servers running a specialized network operating system, or NOS, that manages the network's resources and security.
So when my computer needs a file, it asks the server, not another workstation.
Right. The request goes to the server checks if you're allowed access, authentication and authorization, finds the file, and sends it back to you, the client.
What makes this so much better for bigger environments?
Several key things. Centralized control is huge. Managing user accounts, passwords, permissions, all in one place makes security vastly better and easier. Finding resources is simple because they live on central servers. It's much more scalable, you can add more clients easily, and upgrade servers as needed. And performance is usually way better because servers are built with powerful hardware optimized for handling many requests.
And servers can be specialized, right? Like file servers, print servers, web servers, email servers.
Exactly. Dedicated machines optimized for specific tasks. These servers need robust hardware, backup power, strong security, because if a key server goes down, it affects many users. Most business networks you encounter, and the fundamental structure of the internet itself, your web browser, is a client talking to web servers, are built on this client-server model.
Seems like client-server is the clear winner for most situations, but do networks ever mix these models?
Yeah, our sources do mention that. Many modern networks might be primarily client-server for core functions, but might allow some limited P2P interactions, maybe for specific applications or quick ad hoc sharing in some contexts. It's often a blend.
All right, core idea, check. Scale and types, check. How devices interact, check. Now let's get visual. Let's talk about the actual wires or lack thereof and how they're physically connected, the physical network topology.
Yes, the physical map, the lay of the land, how the cables are run and devices are plugged in. It's important to remember this is distinct from the logical topology, which is how data actually flows. Sometimes they're the same, sometimes not. But physical is the blueprint.
Okay, let's tackle some of the main ones our sources cover. Maybe start with one of the older ones. Bus topology.
The bus. Classic, but mostly historical for LANs now. Imagine one single cable, the bus or backbone, running through an area. Every device just taps into this shared cable, and you need terminators at each end of the main cable.
What was the appeal? Why did people use it?
It was simple, conceptually, and relatively inexpensive because it used less cable than some other designs. Adding a new device just meant tapping into the existing line, which seemed easy at first.
But I sense a but coming. Why don't we see these in offices anymore?
Oh, big buts. Lots of problems. Troubleshooting was a nightmare. If that single shared cable broke anywhere, the entire segment went down. Finding the break could be brutal.
Yikes. One break takes everyone out.
Yep. Very low fault tolerance. Scalability was also poor. Since everyone shared the same wire, the more devices you added, the more they competed to talk, leading to data collisions and slowing everything down. Plus, since all data went everywhere on the bus, it wasn't great for security. So, yeah, largely obsolete for LANs today.
Okay, definitely see why that faded away. How about the ring topology? Devices in a loop.
Exactly. Each device connects directly to two neighbors, forming a closed ring. Data typically travels around the ring in one direction, passed from device to device. Each device often acted as a repeater, regenerating the signal.
Were there any advantages to that circular path?
Well, some older ring technologies, like token ring, used a very orderly method called token passing to control who could send data when. This prevented the collisions that plagued the bus topology, so rings could actually perform quite well, especially under heavy traffic loads, historically speaking.
But what were the catches with the ring?
Similar to the bus, in some ways, fault tolerance was a big issue. If one cable segment broke or one device in the ring failed, it could break the entire loop and stop all communication unless you had built-in complex, often expensive redundancy, like a dual ring setup.
And adding or removing a computer meant breaking the circle.
Yes, which was disruptive. Troubleshooting could also be difficult. Like the bus, you don't really find physical ring topologies in modern LANs anymore. The concept of a ring, though, especially for redundancy, still exists in some high-end WAN and MAN fiber optic networks, like Sonnet's DH.
All right, so if bus and ring had these critical flaws, what emerged as the go-to physical layout for modern LANs?
That would overwhelmingly be the star topology, also sometimes called hub and spoke.
How does that work?
It's simple and elegant. Every single device on the network connects via its own dedicated cable directly to a central point. In modern networks, that central point is almost always a switch. In wireless networks, it's the access point.
Ah, so each computer has its own wire running back to a central box. That sounds much more robust.
It is. Huge advantages. Much easier to install and manage. You just run a cable from the device to the switch. It's very fault tolerant. If one device's cable breaks or the device fails, only that device is affected. The rest of the network keeps working perfectly fine.
Troubleshooting must be way easier, too.
Way easier. You can immediately isolate the problem to a specific device or cable run. It's also a highly scalable need to add a computer. Just run a new cable to an available port on the switch. And performance, especially with switches, is excellent because each connection is essentially a private line to the switch, minimizing collisions.
Okay, seems like all positives. Is there any downside?
The main one is that the central device, the switch, or the access point, becomes a single point of failure for all the devices connected to it. If that central switch dies, that whole segment of the network goes down.
Right, everything relies on that central hub.
Exactly. And it does require more cabling than a bus, since every device needs its own home run back to the center. But honestly, for most situations, the benefits in reliability, manageability, and performance far outweigh those drawbacks. That's why virtually all modern wired Ethernet LANs are physical stars, and wireless LANs inherently function as stars with the AP at the center.
Makes total sense. Now, what about the mesh topology? That sounds like lots of connections.
It can be the ultimate in connections. There are two main types, full mesh and partial mesh. In a full mesh, every single device has a direct point-to-point connection to every single other device on the network.
Whoa. So if you have 5 computers, each one has cables going to the other 4.
Precisely. Our sources note the formula. For n devices, you need n times n minus 1 divided by 2 connections. So for just 10 devices, that's 45 separate cables and a lot of network ports.
Okay, yeah, that sounds completely impractical for a typical office LAN.
Absolutely impractical.
Yeah.
Wildly expensive in terms of cabling and the number of ports needed on each device, and incredibly complex to set up and manage.
So why even talk about it? Where is it used?
Well, the advantage of a full mesh is maximum reliability and redundancy. If any one link fails, there are tons of other paths the data can take. Performance is also potentially great with all those dedicated links. So while full mesh is rare, partial mesh is very common and super important.
Partial mesh, so not connected to everything.
Right. In a partial mesh, some nodes might connect to many others, maybe the critical routers, while other nodes connect only to a few key points. You see this a lot in high reliability networks, like the core backbone of the internet or large WANs connecting major data centers. You get high redundancy on the critical paths without the insane cost and complexity of connecting absolutely everything to everything else.
Ah, okay. So partial mesh for reliability and critical infrastructure. Got it. What about wireless mesh? Is that related?
It is, conceptually. Wireless mesh networks use multiple access points that can all talk to each other, creating multiple possible paths for data back to the wired network. It's a way to extend Wi-Fi coverage reliably over a larger area without running cables to every single access point. It uses mesh principles for redundancy and path selection.
Cool. Okay, 2 simpler ones left, point-to-point and point-to-multipoint.
Point-to-point is the absolute simplest. A direct link between exactly 2 devices. That's it. Could be a physical cable directly connecting 2 computers or 2 routers linked across a WAN, or even a logical connection like a VPN tunnel between 2 points.
Benefits seem obvious. Simple, dedicated.
Yep. Simple setup, dedicated bandwidth between those 2 points. Inherently secure because it's a direct link, potentially low latency.
Downside is just, it only connects 2 things.
Pretty much. It doesn't scale beyond 2 devices on its own. But it's a fundamental building block within other topologies. Each link in a star is point-to-point. Each link in a mesh is point-to-point. And it's very common for specific WAN connections, like a dedicated leased line connecting 2 company sites.
Okay. And point-to-multipoint or P2MP?
This is where you have one central device connecting out to multiple other devices. But unlike a star where everything connects back to the center, here the remote devices typically only communicate with the central point over that specific link, not directly with each other, at least not over that P2MP link.
Can you give an example?
Sure. Think of a wireless internet service provider, the YGSP, with an antenna on a tower, the central point, connecting 2 antennas at multiple customer houses, the multipoint. Or a standard Wi-Fi access point central talking to several laptops and phones, multipoint. Satellite communication also often uses this model. Or connecting several remote buildings on a campus wirelessly back to one main building.
Yeah.
It's efficient for broadcasting information from the central point out to many locations. Can be cost-effective for connecting multiple remote sites, especially wirelessly, compared to setting up separate point-to-point links for each one.
Disadvantages.
The bandwidth from the central point is shared among all the remote points, so it can get congested. The central device is a potential single point of failure. And for wireless P2MP, you often need clear line of sight between the antennas.
All right. And the last topology mentioned is kind of a catch-all, hybrid.
Exactly. Most real-world networks, especially larger ones, aren't just one pure topology. They are hybrid. They combine two or more of the basic topologies we've discussed.
So you mix and match depending on the need in different parts of the network.
Precisely. You leverage the strengths of different layouts. Maybe you have office floors wired in a star topology using switches, but all those floor switches connect to a high-speed fiber ring or maybe a partial mesh backbone that runs between floors or buildings. Or you might have a main star network, and one of the points on that star is the center of another star network, a hierarchical star.
What's the benefit of doing that? Flexibility.
Flexibility and scalability are key. You choose the best, most cost-effective topology for each specific segment or function. It can also improve overall reliability, as a failure in one segment, like one office floor star network, might not affect other segments connected to the backbone.
Any downsides to mixing things up?
The main ones are increased complexity in design and management. You have to understand how different parts interact. It could potentially increase costs if you need different types of hardware or expertise. And troubleshooting can sometimes be harder because the overall picture is more complex.
So when picking a topology, there's no single best one.
Definitely not. As our sources emphasize, it always depends on the specific requirements. You have to ask, what's the budget? How easy does installation and maintenance need to be? What level of fault tolerance is required? What are the security considerations? How much does it need to scale in the future? Choosing the right topology or combination of topologies comes down to answering those questions for your specific situation.
That's a great point. It's about design choices based on needs. Speaking of design, let's touch on a couple other important structural concepts. The network backbone and segments.
Right. When you have a larger network, you almost always break it down. Think of the backbone as the main highway or the spine of the network. It's the central high-speed part that interconnects different network segments or different LANs.
So it carries the bulk of the traffic between different areas?
Exactly. It needs to be fast and reliable, so it often uses high-bandwidth technology like fiber optics. Servers or the connections to different network segments typically plug directly into this backbone.
And the segments are the smaller pieces branching off that backbone, like neighborhoods off the main highway.
Good analogy. Segments are the smaller sections, maybe individual floors, departments, or specific functional areas. The workstations, printers, and other user devices usually live within these segments, and the segment connects back to the main backbone, usually through a switch or router.
Why bother breaking the network up like this? Why not just have one huge flat network?
Several crucial reasons for segmentation. First, performance. It reduces overall network congestion by keeping local traffic within the segment. It also creates smaller collision domains with switches and broadcast domains with routers, which basically means less noise and interference for devices trying to communicate.
Okay, performance. What else?
Security is another big one. By segmenting the network, you can isolate different areas. If something bad happens in one segment, like a malware outbreak, it's less likely to spread easily to other parts of the network. You can apply different security policies to different segments.
And management.
Simpler management, too. It makes the network more organized, easier to understand, and much easier to troubleshoot problems because you can narrow down the location more quickly.
And you can segment physically with different switches and routers, or logically.
Both. Physically separating networks with routers is the most distinct way to create separate broadcast domains. Switches inherently segment collision domains. Each port is separate. But you can also create logical segments using VLANs, virtual LANs. VLANs let you group ports on one or more switches into different broadcast domains, even if they're plugged into the same physical switch hardware. Gives you a lot of flexibility without rewiring.
Okay, so we've designed our internal network with backbones and segments, but eventually it needs to connect to the outside world, right? To the internet service provider.
Absolutely. That brings us to service-related entry points and service provider links. The entry point is just the point where your private network physically connects to the external network provided by your ISP or telecom carrier.
And there's a really important line drawn there, isn't there? The demarc.
Yes, the demarcation point, or demarc. This is critical. It's the precise boundary line where the service provider's responsibility officially ends and your responsibility begins.
So, if there's a problem, you know whose job it is to fix it?
Exactly. It's usually a physical thing, a specific jack on the wall, or maybe a piece of equipment the provider installs, like a smart jack, that allows them to test the line up to that point. Knowing where your demarc is crucial for support and troubleshooting. If the problem is on their side of the demarc, they fix it. If it's on your side, it's your problem.
And the service provider links are just the types of connections you actually buy from them.
Right. The actual circuit or service, we touched on some earlier, could be dedicated lines like a T1 or faster optical circuits, packet switch services like MPLS, Ethernet WAN, standard broadband like DSL cable or fiber to the home, or various wireless options like satellite, cellular data, maybe even dark fiber where you lease the physical fiber optic cable itself and light it up with your own equipment.
Choosing the right link seems pretty important for performance and cost.
Hugely important. You need to match the link type and speed to your actual needs and budget.
Okay, we've covered a ton of ground on traditional network building blocks. Before we wrap, our sources rightly highlight a massive trend that's reshaping networking, virtual networking.
Yeah, this is transforming things, especially in data centers and cloud computing. Virtualization isn't just for servers anymore. It's huge in networking too. The core idea is creating logical network resources, switches, routers, firewalls, entire networks that are independent of the physical hardware underneath.
So just like you can run multiple virtual machines or VMs on a single physical server.
You need virtual networks to connect them. Each VM typically gets a virtual NIC, a VNIC, which is like a software-based network card. These VNICs connect to a virtual switch, or vSwitch, which is also software running on the server's hypervisor, the platform that manages the VMs.
So you can build complex networks entirely in software on one physical machine.
Or across multiple machines, yes. You can create isolated virtual networks for different applications or tenants, all running on the same shared physical infrastructure.
And it goes beyond just switches and NICs, right? You can virtualize other network devices.
Absolutely. That's called Network Function Virtualization, or NFV. This is where you take traditional network hardware functions like routing, firewalling, load balancing, WAN optimization, and run them as software applications, often called virtual network functions, or VNX, on standard off-the-shelf server hardware.
Instead of buying dedicated physical boxes for each function.
Exactly. Instead of racks full of specialized hardware, you run these network functions as software on powerful generic servers.
What are the big wins with virtualizing networks like this?
Agility is massive. You can spin up new networks, deploy firewalls, change configurations almost instantly through software instead of physically wiring things. It leads to much better resource optimization and cost savings, less dedicated hardware to buy and manage.
Scalability must be easier too.
Much easier. Scale up or down by allocating more or fewer software resources. Security can be enhanced through microsegmentation and isolation within the virtual environment. Management is often centralized and automated through software controllers, and deploying new services becomes much faster. It's really fundamental to how modern data centers and cloud platforms operate.
Wow, so you can literally construct intricate network infrastructures that barely have a direct physical counterpart anymore.
It's a major shift, yeah. Adds a whole layer of abstraction, flexibility, and automation on top of the physical network.
Okay, that was quite the journey. We really covered the landscape. We started with that simple idea, devices connecting to share stuff.
Then we explored that whole spectrum of network types based on size and reach, from the tiny pan around you, the familiar LAN at home or work, the CAN on campus, the MAN across the city, right up to the global WAN like the internet, and those specialized SANs for storage.
We looked at the how of interaction, peer-to-peer versus client-server architecture, and why client-server really dominates for anything beyond the smallest scale.
Then we mapped out the physical shapes, the topologies, the old bus and ring, the now standard star, the super reliable mesh, especially partial mesh, the basic point-to-point, and the broadcast-style point-to-multipoint.
Recognizing that most real networks are actually complex hybrid combinations, mixing and matching these basic shapes.
We also hit on key design ideas, breaking networks into segments connected by backbones for better performance and security, knowing your demarcation point with your service provider, choosing the right external links.
And we finished by touching on how virtual networking is fundamentally changing the game, allowing us to build and manage networks in software.
It's truly foundational knowledge, isn't it? Understanding these basics is so helpful, whether you're just trying to figure out why your Wi-Fi is slow, navigating a corporate network, or even just appreciating the magic behind clicking a link online.
Absolutely. It gives you the vocabulary and the core concepts to make sense of so much technology around us. So here's maybe a final thought for you to chew on as you go about your day. Just stop and think for a second about how all these different layers we talked about, the physical cables maybe under your floor, the logical connections, the rules for how devices talk, the servers and clients, the different network shapes, the routers connecting everything across the globe, and now even these virtual networks running as software how all of that complexity works together, mostly invisibly.
Yeah, all just to let you load that web page or send that quick message.
Exactly. How much hidden, intricate infrastructure are we relying on truly every single second we're connected?
It really is pretty remarkable when you break it down.
Indeed it is. Well, thanks for joining us on this deep dive into network shapes and sizes. We really hope it helped clarify the interconnected world we all live and work in.